excellent food and lunch you've just had. We're into the final stretch, and once again I'm very pleased that we are going to be talking about something obviously related to some of the things we've been covering for the last 2 days, but actually something a little bit new, focusing on ultra-fast charging. And for that we've got Professor Rufer, who's a professor at the Professor of Industrial Electronics at the Federale Ecole Polytechnique in Lausanne, Switzerland, which is also the same institute that he graduated from. He's an author or co-author of over 200 publications and has won not one but 2 IEEE prizes. So we're very privileged to have him this afternoon to talk to us about some of the challenges and solutions of ultra-fast charging for electric vehicles.
So good afternoon, everybody. Thank you first to the organizer for inviting me to participate to this very interesting future mobility program. I'm going to present you some results of a research program, a relatively important research program we led at Lausanne EPFL together with other colleagues from Zurich and from Lille, other schools in Switzerland. And the studies dedicated to the fast charge of electrical vehicles. So I will begin my presentation by showing you some very important differences between charging an electrical vehicle and fueling a classical gasoline or diesel car. Then we will go to the state of the art of the possibility for infrastructure for charging. What can we get from the outlet? What is the access to the car? And then we will have a look to the requirement on the vehicle of the battery regarding power, regarding efficiency. And then I will present you the concept of what we call the intermediate buffer. And then we will go to some different aspects. It is a multi-port charging station. Of course, fast charge has no sense to be developed for home application. It is typically dedicated to charging on the road. So we will have to develop some fast charging station where you can charge several cars in parallel and to solve the problem of the power interface to the grid. Then I will present you in this context some novel architecture for the solution of these fast road charging stations. As I said, the research program was called Ultra-Fast Charge of EVs. You see the partner here on this picture. For those who are interested, there is a web address ufcev@epfl.ch. You can find many technical reports dedicated to that project on this address. So let me begin my presentation with this evidence regarding the difference between a battery or an electric car and a gasoline car. By the electric car, of course, you have some constraints. In principle, you cannot charge a battery faster than you can discharge. This is a limitation on the electrochemistry. And you see typically for the gasoline car, the totally different context. You are driving a long time with a reduced power, and you are refilling with a very, very huge amount of power. If you calculate that you are fueling a limousine with around 50 kilograms of gasoline, the energy value of the gasoline or the diesel is 42.5 megajoules per kilogram multiplied by 50 kilograms. If you fill that in 2 minutes, 120 seconds, you come to the impressive power of 17.7 megawatt. In the electric car, the battery of the car is totally impossible to achieve such a kind of power on the side of the car, and of course the grid or the connecting point is not able to deliver such a power for an electric car. So we have to have a look to what is the meaning of the speed of charging the battery. First, let us have a look to the possibilities. We have distinguished 4 different types of interconnection of charging. The charging modes, the mode 1 with 3.6 kilowatts, the mode 2 with 7.3, the mode 3 with 14 kilowatt, independently of the current you have, and what is interesting, the 4th mode, that is a DC charging that can go up to 400 amps. And you see the main difference between these chargers. The 3 first are on-board chargers, and the 4th possibility is an off-board charger. And this is evident that for a very, very high power charger, you will not have an additional weight corresponding to that power in the car. So it is of importance to have an access directly to the DC connection of the car battery for being able to charge fast. Here I have another comparison or another parameter that is also very important regarding the autonomy or the range you can drive with the car. Here we have defined what we call the autonomy flow rate. The autonomy flow rate is the number of kilometers with its equivalent of energy you are able to charge, to give to the vehicle within a given time. You see, typically with a domestic one-phase charging, you are able to provide to the car 0.3 kilometer per minute. If you charge the diesel or if you charge a gasoline car, you can charge 600 kilometers within 1 minute of charging. And this is a little similar concept as we have seen tomorrow. People have spoken about the distance between fueling stations. Here you see typically it is also important to be able to distinguish, is it important to have a long autonomy, or is it important to have a very fast charge opportunity? So the requirement on the battery. This is also a very important representation. You see here clearly that you cannot do everything you wanted to do. This picture shows the needed power you require for charging a 25 kilowatt hour battery within a given time. You see, the small charging time is automatically related to a high power demand. And if you go on the time scale for the times that are under the 20 minutes, you see that you can come to very, very huge amount of instantaneous power that you are soliciting the grid. This is a problem not only for the battery, this is a problem of the availability of the interconnection point. And this has been the main reason of defining what we call the intermediate buffer. The intermediate buffer system has a low power charger that is charging a local intermediate buffer, and when the vehicle comes, you have a very high power exchange, this arrow, where you have defined only a fast exchange of energy between the local buffer at the station and the car. The second issue regarding the requirement is what happens inside of the battery. And this is a property you see typically independence of the value of the internal resistance of your battery. You can run into a domain where you have really crazy values of the energetic efficiency when you go too fast and we go too high in the instantaneous power. This is also a condition that gives what you have to do inside of the battery. Poor efficiency means a lot of loss inside of the battery, and it is very important for fast charge to have a very, very well cooled battery during this fast charge process. Then we have gone in the direction of the road multi-port system, multiplying the number of ports. If you look a little in detail to my picture, you can see that it is composed of several pictures by mouse click, zoom, and putting together, you can multiply very, very easily the number of connecting points. But in reality, you cannot play with the mouse. In reality, you have to solve the real problem of energy, the real problem of the power. And here you can say that for multiplying fast stations, fast ports in a station, you are clearly in the megawatt range, and in the megawatt range you should start to play with low voltage distribution. You have to go to an interconnection to the medium voltage grid. The question is how to design such a system. And here we have gone to some analysis of what happens in reality. You see that the analysis is based on a lot of statistical approach, stochastic approach. First of all, we have looked what happens on the road, what is the number of vehicles, and you see here some statistical results. The blue bars correspond to a place on a highway in Yvermont, in Switzerland. The red one, they correspond to a place inside of the city of Lausanne. And you see there is a similar picture of the traffic density if you are on a highway or if you are inside of the city. And you see the typical peaks or in the morning and in the end of the afternoon. Second aspect that you have to consider, that you have not all vehicles with the same capacity to charge. So you have a distribution. Here we have taken some statistical results about the capacity of each vehicle. This is the first line of this slide. And then the second line illustrates that not everybody goes to the charging station with a fully empty battery. This is a very, very important parameter. Some people come with 50%, some people come with 20%, some people come with 10%. So you have to take into account all these different conditions of the real world of the people coming to the fast charge station. So you can then play with this statistical result and make a kind of evaluation of what will happen. You see the blue curve. The blue curve is what can happen on at the place where you accumulate statistically the different type of the car and also the state of the charge. You have the opportunity to do some filtering with this integrated buffer. And so here you have also a very, very large degree of freedom. You can decide to just level the power peaks, but you can also, this could typically correspond to the red curve here, where you are smoothing the consumption here by the car statistics. Or you can go to the domain where you design that buffer with a much more higher capacity in order typically to have some shift here. A great part of the power that is transferred to the vehicle is pre-charged during night hours. This is typically this green curve. With our analysis, I will not go too much in the details. You can try to evaluate typically here the buffer capacity, independency of the number of vehicles per day at a given place. You can define the connecting power of your buffer. You can also choose a number of ports that are needed to satisfy the demand with a given value of minimum or maximum waiting time at the station before you will be able to charge your vehicle. So let me now present you some novel architecture proposal. You see here we have considered two different conditions. First, the charger station with multi-port architecture. You see here that you can charge different vehicles. Here there are only 3 represented, but you can go to a higher number. And another interesting aspect is that we define a configurable output. So you can typically decide to make a fast charge of n vehicle, n being a relatively limited number, or if you don't have the demand of fast charging, you can charge m larger amount of vehicles with specification of a slower charge. To this architecture here, I apologize for being too technically too detailed in technology, but I have spoken before on the connection to the medium voltage grid. And a traditional connection to the medium voltage grid will be to use a medium voltage to low voltage transformer. This is an additional element that brings additional costs, that brings an additional affectation by the efficiency. And the concept we have studied is using what is called the cascaded edge bridges concept. I will come on the detailed scheme just afterwards, where we have a possibility with our converter and our system to be directly interconnected to the medium voltage grid level. And of course, with multiple output DC-DC converters, you can then choose the configuration to charge your vehicle. When we have looked to this topology, that system uses a series of modules. The nature of the module or the topology of the module of one H-bridge module is represented here. So by combining series connection of such modules, you can benefit what we define here as a multi-level waveform that has a typical very, very low harmonic content. This is of big advantage when you interface to the grid, that kind of system. And then another idea in this concept is what we call the split intermediate battery. If you speak on local storage with buffer batteries for the megawatt range, you will have to use huge batteries that addresses the question of the reliability, of the security, and so on. And in such a concept, you can split that battery in different levels, in different phases, and then you have the freedom with all these isolated converters to feed the different vehicles as they are represented here with one pair of industry. Another version, but this is based also on multi-level. This is what is called the modular multi-level converter topology. This is a well-known technology by power electronic converters in the HVDC especially. And here you benefit, in addition to the previous solution, to the possibility to be interconnected on a medium voltage DC network. So in future, the people expect to realize distribution on the base of DC, especially medium voltage DC, as it is realized today for the high voltage DC application. Here, another configuration that has also the same advantages, that have also the split buffer and also the possibility of the configurable output in direction of different number of cars or different types of charging speed. So here, just a small call to manufacturers, car manufacturers, but also for investors. There are opportunities for investment. We have a small company, startup of my lab that has in the focus to develop this and to industrialize that kind of modern concept. So, in our research project, of course, we have not stayed on the pure simulation or theoretical result. We have gone to a demonstrator. We have realized a real system. We have realized a system with a limited input power. We have set maximum solicitation of the grid at 21 kilowatt. This was defined by the connection. Then we have designed an intermediate buffer, a relatively large intermediate buffer of 29 kilowatt hours. And then the power electronic circuitry that is able to make the fast transfer, we have designed it for 220 kilowatt. And this has been realized in the form of a movable demonstrator. It's a trailer. You see here a view of the side of this trailer with the fans. The fans indicates also that you have to cool correctly your battery for the high power solicitation. Just a picture of the rear view and also a picture of inside of this trailer with, you see here that many different batteries that are put together in a modular form in order to be able to provide to the car the needed high power of the system. So, as a conclusion, fast charge of EVs is demanding specific design regarding power density. We have to solve the problem of the power demand from the grid. We have also to consider efficiency issues. We have made a detailed analysis based on statistics, allowing the design of multi-port installation regarding buffer storage capacity for limited power demand from the grid. There are new concepts that are developed and can be industrialized for large charging stations. And the demonstrator shows you the picture of the realized equipment. So, thank you for your attention.
Thank you very much indeed, Melissa. Any questions at all around that presentation? I've got one question for you, which is, obviously you're doing this research as part of a university institution. To what extent are similar research or work being done, perhaps either by battery manufacturers or vehicle manufacturers, for example? Is this still the preserve of academic institutions, or is it more widely being commercialized?
Today there are many actors in this field, but maybe in the side of the accumulators, people are relatively deeply involved in electrochemistry technology, and we know our colleagues from the chemistry, they are more basic science and not engineers, or not application engineers also. On the other side, the car manufacturers, we can say in many companies, the deciders or the managers are more issued from the world of the, let's say, mechanical engineer, and the power electronicians or the electrical engineers, they are not involved deeply as industrial actors in this world. Of course, companies make a lot of progress, companies make a lot of investment, but at the university, this is a very agreeable position. We take the liberty to look, we have seen some approach from Imperial College, many universities, they propose that then industrial world can use it if they are interested.
So it's very much led by the academics. Yes.
A quick question regarding the effect on the batteries due to fast charging instead of regular. Just a quick question in terms of the maybe negative effect on batteries with high-speed charging instead of, I don't know what slow is anymore today, but you know, with the 15-minute capabilities of charging to maybe a 4-hour capability, the effect of lifespan of the battery, has that been looked at? Have you seen any effects, or does the battery technology change that it doesn't matter anymore?
Of course, there is a much more higher solicitation of the electrochemistry inside of the battery. Now, there is a first aspect that is evident, that you have to stabilize the temperature. You have to limit the elevation of temperature. This is maybe the first big gap to cover, and you have. We have seen this some needs from Ford regarding cooling of the batteries, but the context was use of the vehicle, not charge, not fast charge of the vehicle. But this is similar technology demand. If you charge fast, you have to be really, really careful by eliminating the loss inside of the batteries. But in our study, we have not gone too deep. We we have solved the problem in the framework of our demonstrator. You have seen this is a very well-cooled system. It is an established battery technology, but we have not investigated exactly what happens inside of the battery. But I think thermal aspect for aging is fundamental. Then by discharging fast, you can go relatively high without causing electrochemistry damages. By charging is different because by fast charging, you elevate the voltage, and on the electrochemistry, something can happen when the voltage dissociation effect and things like that on the battery. But we speculate also, you know, today, practically every month we hear from new materials for electrodes. Today we benefit from LTU technology that is really performant, much more performance than we had, let's say, 3 or 5 years ago. So we suppose that batteries can perform battery.
Any other questions at all? Okay. Thank you very much. I think you want to stay with us for the